Hey, good morning, everyone. So today we will have the presentations of Senior Project 2 for Spring 2024. We will start with the first presentation, which is the project title Plagiarism Detection Tool. You guys have 20 minutes, and then we will have 10 minutes for questions. Okay, thank you. Go ahead.
So good morning to you all. We stand before you today to share with you our thesis project, a plagiarism detection tool that's made specifically for AI-generated text. But before we dive into our project, allow me to introduce our brilliant team. Amy Samy, Jessica Mansi, Miriam Youseef, Mohamed Afifi, Mohamed Hashish, and I, Sherif Wessa. So this is our agenda for today. So in an era dominated by artificial intelligence, the question of authenticity becomes very complex. Our journey begins right at the intersection of AI with academic content. And our goal and our team has been dedicated to craft a solution that safeguards the authenticity of academic content. The current existing detection tools struggle to efficiently detect AI text, mainly because of the effect of plagiarism, paraphrasing and humanizing. And this is where our tool steps in, designed to be a robust plagiarism detection tool that's capable of identifying AI text, providing educators and institutions with powerful ways to uphold academic honesty. And now Miriam will walk us through the objectives and the guiding pillars of our project.
So our main objective for our thesis project, the final one, is basically to develop an API tool that has a robust web-based interface to detect the AI content. Walking the extra mile in making this tool enhanced by introducing it to paraphrased content for detection, as well as addressing the challenges and the differences in the AI text and the human written text by creating an API as a platform. Moving on with discussing more about the data sets with Mohamed.
So data sets are crucial for model training because data sets are required to train models. So in order to train our model, we had to acquire some data sets. So starting with our English data set, the task was relatively easy because all we had to do was look for the best fit. And that we found on Kaggle in a comprehensive data set that contained AI-generated text from multiple sources. All we had to do was some data cleaning, trimming, dropping duplicates, and balancing, and then the data set was good to go. As for the Arabic one, that's where we faced some challenges because of the scarcity of the available online data sets. So in order to overcome that obstacle, we had to acquire our own data sets. So after some digging, researching, and looking around, we finally stumbled upon one extracted from an Omani newspaper. Then the challenge of obtaining Arabic human written text was done. But still, we had to overcome the challenge of generating AI Arabic text. So we used the API of. Then, using paraphrasing tools, we were able to acquire some paraphrased data sets. Then, using the Gemini API tool, we were able to humanize some data sets. So after getting the data sets, it was finally time to move to our next step, which is training models. So for our models, we decided to use BERT and LSTM. BERT is a pre-trained model developed by Google, and that it can be fine-tuned to acquire some certain tasks, and that we did for text classification. And LSTM stands for long short-term memory. Long short-term memory. However, it was not pre-trained, and we had to implement it from scratch because it was purely mathematical using tanh and sigmoid functions. So for our English models, we used the three to do ensemble, which will be BERT based on case, BERT for sequence classifier, and LSTM for Arabic. And for our Arabic models, we used BERT mini Arabic and LSTM for Arabic. So let's dive then into their architecture. So BERT is built on top of transformers model, but instead of using encoders and decoders, BERT utilizes only encoders, and it stacks them on top of each other to contain something called an encoding layer. This encoding layer gets text, and then the text is tokenized Then embeddings vector is produced. Then it's passed to a dropout layer to drop out some essays to ensure that our model is actually learning and not just memorizing. Then the output of this layer is passed to our softmax layer to determine whether it's AI generated or human written. I leave you with a deeper understanding of architecture of BERT with Miriam.
So there is a situation where probably our professors encountered before receiving an email and kind of having the sense that this email is generated by ChatGPT, not authentic from the student. And I'm here to discuss in depth how our models also interpret this kind of sense or feelings. I want to start basically first by going in depth in the DistilBERT model. We intentionally chose DistilBERT as it has 40% less architecture of a larger model called BERT, yet it keeps and maintains almost the same performance of the original BERT. Also, it uses a training method called knowledge distillation, which allows it to learn the things in the same structure of BERT while maintaining the less architecture. Also, DistilBERT is designed to be fast and quick, which makes it easy to be deployed on devices that has less computational powers, which makes it like a real-time application. And throughout our explainability experiments, we found that there are three main highlights and layers that DistilBERT depend on and work with. Firstly, the internal representation layer, which works for transforming the words into embeddings. The second one is the attention mechanisms that focuses on different parts of the feature to better enhance the model's predictions. And finally, the fine-tuning of the model. And now we're going to discuss the LSTM architecture with Mohamed.
So as stated earlier, the LSTM architecture utilizes the 10H and sigmoid functions. So LSTM architecture is divided into several key components, which will be the forget gate, which determines how much of the information should be discarded before moving on to the next one. And then we have the input gate, which determines how much of the information it should allow. After that, we have the cell state, which is the memory of the model itself. And then we have the candidate cell, which will be the next cell in order. The input of the candidate cell will be a hidden state. Then the hidden state is passed to the candidate state. Then an output is produced that is extracted from an output gate. Okay, and now I'll leave you with a deeper understanding of LSTM architecture with Miriam.
Okay, so LSTM is a type of neural network that learns very well on long periods of time, makes it ideal for sequences, aka sentences. We created the LSTM model from scratch, which makes it authentically our own. And we ran three main explainability experiments on it. The first one is the feature importance using a library called Trip. What does it do? Mainly, it analyzes the features of the input text in the datasets and create a graph that basically highlights the importance of each features on the predictability of the models. We had about 120 features. Our 5 top features was the word frequency, as there are some sets that are most likely to be used in the AI generation while rarely used in the human written. The average number of words used in a sentence, the n-grams, which are the combination of words together, the variety of different used words, and finally the sentiment consistency. Another experiment on also the feature important characteristic is the permutation features, which analyzes the efficiency and the predictability of the model by shuffling the features all together and see and notice how the performance of the model decrease or increase. The high charts represent the most important features and the low bars represents the low ones. Finally, for the internal architecture layer analysis, we ran another tool that is the integrated gradients, and we noticed that The three significant outputs of this experiment was the number of parameters in the embedding layer, which is about 12 million parameters, the efficiency of the bidirectional layer in capturing the essence of each text and the sentence as a whole, and finally, the importance of batch normalization and the L2 regularization. Now, moving to discussing the final results of our models with Mohamed Hashish.
So now we'll talk about the results of our English models. The first model is the BERT-based uncased. It actually, the performance was very good. It detected or differentiated between the human written text and the AI generated text with a percentage of 98%. It also captured the paraphrased one with an accuracy of 95%, as well as the humanized with an accuracy of 98%. And the humanized text is an actual AI text with some added emotions and words that humans tend to use usually. For our second model, the still BERT-based uncased, its performance was very close to the previous one, except that it couldn't detect the paraphrased text efficiently as the last one with an accuracy of 81%. And this was actually expected since its architecture was relatively smaller than the BERT-based model. And now our model, the LSTM English that we've created from scratch, it performed very well actually and outperformed the still BERT in detecting the paraphrased text. And all of these results actually show how efficient our models were trained and how they are able to capture and differentiate the AI text and the human text.
So after discussing our English results, let's move on to our Arabic results. So we divided our Arabic data set, which consisted of around 39,000 Arabic essays, into training, validation, and testing with a ratio of 80 to 10 to 10. So for BERT Mini Arabic, this model actually performed quite well when tested on a balanced data set, which consisted of human written and AI generated essays. Its accuracy, its F1 score was around 96%. However, its performance dropped significantly when tested on paraphrased essays. It dropped to 64%. And as for the humanized, it performed better as the F1 score was around 93%. So that's why we retrained our model on paraphrased essays. So let's look at the improvements after training. So the F1 score slightly increased for the human written and AI generated essays, but the most significant improvement was observed when tested on the paraphrased essays, as the F1 score jumped from 64% to around 95%. As for the humanized, it also increased to 98%, and this was because the humanized dataset we used was from an LLM from Gemini, an LLM developed by Google. We asked it to make the essays humanized or indistinguishable from human written texts. As for LSTM Arabic, this model scored an impressive F1 score of 96% when tested on human written and AI generated essays. The F1 score slightly decreased when tested on paraphrased essays, and it performed much better for the humanized dataset as the F1 score was around 98%. So generally, this model improved, scored better scores than distal BERT.
So now, after discussing the model architectures and displaying the results of all of our models, there are some encountered issues that we'd like to address. First, we focus on 4 different metrics: F1 score, recall, precision, and accuracy. But our main focus was on the F1 score since it's commonly used in binary classification problems, just like ours. And when we first ran the pre-trained model and trained them on our own data set, we got very, very high numbers of 99% almost, and this raised some questions among us. So we decided to investigate these numbers by applying different data pre-processing techniques and different splitting ratios, different cleaning functions. We also use different data sets to make sure that our data set is valid and that the problems are in the models themselves. We printed the train loss and validation loss, and we actually concluded that it couldn't fit the data correctly into the model since it's very large. We plotted the train and validation accuracies also to see how the model performs. And the major issues detected were an overfitting, that all our models are actually overfitting. So moving on, how we achieved these results and how we fixed these issues. We started by fine-tuning the hyperparameters and introducing dropout rates. We added attention dropout layers, which drops some of the transformers architecture from the BERT itself. And also neurons drop out the neurons from the deep network. We added some regularization. Besides the weight decay, which is already introduced, we added manual L2 regularization to penalize the model whenever it starts to overfit and to force it to fit the data correctly into the model. We adjusted our own learning rate to be relatively small to make sure that it captures the most important features of the text and not and to avoid the problem of overshooting and missing some of the important features. We used the correct bias parameter to make sure that our model is actually not biased towards either human text or AI text. And we applied different text cleaning techniques as pre-processing steps in splitting ratios and applying different cleaning functions so that the model be able to train on the data efficiently. And finally, we chose different batch size to make sure that the model runs efficiently. So these are the graphs before fine-tuning the model. As we can see, there's a huge gap between the validation curve and the training curve. These are the accuracy plots, and this shows a very high overfitting for the model. It cannot generalize. It tends to memorize or work closely to the train data set. But finally, after so many trials, we actually succeeded in reducing the gap significantly between the train curve and the validation curve to make sure that the model doesn't overfit and actually learns and not memorize the trained data sets, but it captures the important features and be able to distinguish and differentiate between AI text and human written ones. So now we'll discuss the model testing.
So after we achieved the results we got for our models, we wanted to make sure of our results. So now let's discuss how we tested our models. So we first performed a data corruption experiment. Our training data set had labels of either 0 or 1, where 0 represented human written essays and 1 represented AI generated essays. So we randomized these labels for our training data set, and then we tested our models on correctly labeled data. The models performed very badly as expected. For example, Distelbert had an F1 score of 67%. This experiment was done to ensure the quality and trustworthiness of our models. We then compared our English models with one class, which is a pre-trained model that uses feature extraction for plagiarism detection. One class had a precision of 82%, a recall of 74%, and an F1 score of 72%. The 3 of our English models outperformed one class in terms of F1 score and recall, and BERT-based uncased and Distelbert exceeded one class in terms of the precision.
To further test our model, we got a larger data set, which makes we test our model on its robustness and general applicability on real-world data. This, with the data set of 360,000 essays, which is much more than our training data set, we tested each model individually. We got the models did not disappoint, with BERT based on case giving 91%, Distelbert for sequence classification giving 84% F1 score, LSTM got a 93% F1 score, and then we tested them on the ensemble, which will be our final product, and the ensemble performed the best with a 93% F1 score. Now Amy will be talking about the explainability.
So after the models showed that they have strong detection capabilities for detecting AI-generated content, so we decided to delve deeper and see how actually the models are able to classify the AI-generated content correctly. Next slide. So we wrote code for feature extraction that extracts around 40 linguistic features for the essays. These features fall under 5 categories: text repetitiveness, part of speech, readability, and sentiment analysis. And our analysis showed that human written text tend to have more numerals, determiners, and adverbs, enhancing rich descriptive language. It's also more complex and varied as it has longer sentences. On the other hand, AI-generated texts tend to have more commas, potentially because of the structured generation processes. And there were also some features that did not really matter, such as the number of paragraphs and the number of full stops. But AI-generated text tended to have more readability scores. So these features helped us distinguish between human-written text and AI-generated text. So we saw how the model is able to classify the text and which features are more important than others. So now Sherif will be doing our demo.
So, and now is the demo of our product. And now is the demo of our product. We have a one-shot video recording that proves how efficient our product is. So as you can see, for the convenience. So back with our demo. So we just copied the response of ChatGPT and directly pasted it to our tool. And as you can see, our tool successfully detects that the text is AI generated and highlights the sentences that is most suspected to be AI generated. And for a comparison, we chose Zero GPT, which is a very popular and trending AI detector. And it also can detect that it is AI generated. For addressing the paraphrasing effect, we chose Paraphraser.io, which is the second most popular paraphrasing tool. We gave it the text that we got from ChatGPT, and we're waiting for it to paraphrase. Then we copied the paraphrased version and directly pasted it to our tool. And yes, our tool can still detect that the paraphrased is also AI generated. Let's see if Zero GPT will detect it. Surprisingly, Zero GPT fails to detect that the paraphrased version is AI generated. And now for the negative scenario. This is my Red 1020 paper, and you can see that it was last modified 3 years ago, almost before the creation of ChatGPT. Let's paste it to our tool. Our tool can identify that the text is AI generated. Is human written.
Now we're gonna be looking at the Arabic version of the same thing. We also asked ChatGPT to write us an essay. For this, we did not compare it to Zero GPT because in general, all the detectors, the popular detectors out there, do not classify Arabic text properly. So we copied the text from ChatGPT and we pasted it on our product. And it classified it as 100% AI generated. We're gonna now test it on human written, on paraphrasing first. So we first choose the Arabic language to be able to properly paraphrase it. So we copy the paraphrase text and we paste it into our model. And it also still detected it as 100% AI generated. Finally, we got a human written essay from Wikipedia that was done in 2020, which is before the creation of ChatGPT. So we're sure that it was human written. And we pasted it into our product and it gave 0% AI generated.
And now for the empowerment outcome, as we stated before, we decided to have a product as well as a research paper. So our user interface is developed using the React.js library, and the API backend is built using Python and Fast API framework, which is known for its performance and scalability. And this is the approach that we follow. Starting with the user providing an essay that they want to check for. Initially, the system identifies the language of the submitted essays. And we have two main categories, basic and advanced. For the basic approach, once the language is identified, the essay is processed to our ensemble of models, which employs a max voting strategy where each model predicts an outcome, and the majority vote dictates the final output. And you may ask, why did we make an ensemble if each of our model already performs relatively well? Why don't we just pick one? And our answer to this will be mainly because of the sensitive nature of academic integrity. Our goal is to minimize the risk of falsely flagging a student's work as plagiarized. And for the advanced detection, it's basically an extra layer of investigation. It begins with checking if a prompt was provided. If not, our system communicates with the LLM API to generate a prompt for the essay, and then based on the prompt, it generates multiple essays that is then compared with the submitted essay to using the cosine similarity matrix. And the final output is, and the final decision is the weighted average of the cosine similarity score and the model's prediction. And now Jesse will walk us through the research paper.
So as an empowerment outcome, we got also a research paper. So we focused on the research question. What are the effects of paraphrasing and humanizing tools on the detection of AI-generated text? We propose our different architectures for the plagiarism detection and compare all our different models. As you have seen, we've done many experiments. So we document all these experiments and interpret the results. Okay, next. Next, since we are doing a product, we also did a business model. So for our business model canvas, our main value propositions is we are proposing a detecting AI-generated text content detector that is immune to paraphrasing and humanizing tools and is available in multiple languages, which gives us an edge over our competitors. We are planning to do our own website where students can check their own essays, but also partner up with educational institutions and submission platforms so that we are able to automatically detect whether the text is AI generated once the student can submit. And that's it. Miriam will say our conclusion.
So finally, ladies and gentlemen, as we proudly stand today after the long, remarkable journey full of dedication, hard work, and learning, we successfully maintained to develop a well-integrated API with a robust web-based interface. I would like to share with you the next goals. We're planning to deploy our tool on a server to make it accessible to a broader audience, making it more scalable. And I'm glad to share that we're planning to submit our research paper into the next IEEE conference that's taking place this December on machine learning applications, sharing our findings with the scientific community. Thank you so much for your time.